Hello, my name is Matthew Perkins. Today I will be presenting on a research paper presentation, DUF, for device authentication and secret key generation. Now, this article was a very interesting one, and it is very heavily focused on, again, device authentication and secret key generation, mainly RSAs, RFIDs, and certain things of those natures. Now, first of all, I want to ask a question to all of you. Do you know what a PUF is? And I'll get to this later. Do you know what integrated circuit is? I'll give you a few seconds to think about if you know what they are. Okay, now that we have thought for a little bit, I will actually explain what a PUF is. PUF is a physical unclonable function. It is a device that takes several bits of input and spits out a couple bits of output that now generates a secret value that is used for key generation, that is used for device authentication, other things of that nature. Now, this physical device is used, again, like I said earlier, uses several bits of input and has a couple bits of output. And in between those inputs and outputs, this data, whatever the inputs are, have to go through logic gates and ultimately a latch to return the value of the output bit, which is either a 0 or 1. And in these logic circuits, there are OR gates, there are XOR gates, and there are a lot of different logic gates to be able to return a value that is secure. Ultimately, it is a physical unclonable function. It wants the value in the device to be unclonable so that the device authentication and the secret key generation remains secure. This is a huge thing in cybersecurity where you're going to get a device that gives you a RSA token and a two-factor authentication token, and based upon these two things, you will get a secret value, and this secret value will then give you RSA token, which allows you to get into your devices or your accounts. Now, I've talked about what physical unclonable functions are. They're a physical device that has several bits of input, goes through a logic gate and several different mutexes, and finally gets to a latch that then determines whether it's what the output bits are going to be. Finally, now that you know what the output bits are going to be, it allows it to make a RSA token. Now, you must think, hey, why were PUFs designed to be made when there's already a system, integrated circuits, that is being used for a lot of RSA tokens, a lot of RFID cards? Why is PUFs, why were they designed? Why were they researched? And I will give you a second to think about why a PUF, which is a very simple input and output logic gate that has several different OR gates or XOR gates, no matter how complicated they are, why is this needed? I'll give you a few seconds to think of why. Okay, now that we've thought about it, they were needed because you need a more secure than ICs. Integrated circuits. Integrated circuits are a system that stores a secret value in the virtual RAM of the device. This secret is then used to generate an RSA token, generate different RFID tokens to be able for people to get into their accounts, or to get into the devices. But because it is stored in virtual memory, it is hackable. A hacker is able to, if they are able to find the exact memory slot that secret is in, they are now able to get into any device that you own. They can get into any device that requires RSA authentication. They can now replicate it. Once they get your password, once they get login credentials, the RSA token that's supposed to protect accounts, the hackers can bypass. That is a incredible security risk, and that is why PUFs were designed. PUFs, as stated before, are simple. They are bits of input that go through a logic gate, several logic gates, to finally make it to a latch that then has a couple bits of output that generates a new secret value that can then be used for key generation. It can then be used for RSA tokens. It can be used for any of those authentication methods. Ultimately, what authentication boils down to is you need a secret value that you then encrypt and then decrypt to be able to get a secure token to get into accounts. And so that other people can't get into the accounts that you own. Is another safeguard. PUFs make it so that the only way you're going to get through that authentication is not by going through the virtual RAM, the virtual memory that the integrated circuit goes through, but instead by cloning the machine, the PUF that it is, because you need to know the exact OR gates, the exact XOR gates, the amount of bit inputs, the amount of bit outputs. You have to know all that information, including also the timing of how fast data gets through each of the different paths. It's a lot of information to keep track of, and for different PUFs, it's different information to keep track of. And because of that, you have to now make your own machine to replicate it rather than just having a secret value that you found in virtual RAM. Now that we understand why PUFs were designed and that they are a bit more secure than integrated circuits when it comes to hackability, now let's go on how they work. Like I say, this is an example of how PUFs work. They take a couple bits of input and they spit out a couple bits of output after going through an extended logic gate. Here is a very simple 2-bit input to a 1-bit output. And based off the results of what data bit gets to the D data point for the latch faster, will be given a 1. The other will be given, and if the other one makes it, the output bit will be a 0. And based upon those physical factors, a secret value is made. Now, this secret value is then massaged into several different RSA tokens and certain of those natures. And you might think, hey, isn't it easy just to make a circuit once you find out the rough paths that the circuit will take? Isn't it easy to replicate it? And that's where the XOR gates come in. If you put some of the gates as OR gates and some of them as XOR gates, it makes it so much more complex to be able to replicate because you don't know which value is which. And that doesn't even talk about how our PUFs actually work. Because integrated circuits have to be on all the time. That's how they work. And because they're on all the time, you're able to access the RAM all the time to search for that secret value. That gives hackers a very big time frame to access and infiltrate and try to find that secret. PFs don't have that issue. PFs only turn on when inputs are given in and inputs are given out, and it shuts off. This gives a hacker a very small time period to calculate the speed, to calculate the inputs, to calculate the XOR gates, the AND/OR gates, the X gates, any logic gate. It takes a lot more time for the hacker to analyze this device and replicate it than if they were to just shuffle through different registers of RAM for the integrated circuit. And now that we understand how this PF works, which is inputs through a extended logic gate into a single output, we can now talk about other types of PUFs. There is a ring oscillator PUF. The ring oscillator PUF is a PUF that relies instead on the speed that goes through and determining what the value is based off the speed of going through those logic gates and which data bit goes through those logic gates. It just instead determines it on the oscillations and counter system. This allows it so that the system is a bit more complex than the basic, just regular XOR gates, OR gates, and just relying on data bits and speed. Now, the issue with this is that there are a limited amount of oscillations. The limited amount of oscillations means that there's a lot less inputs that you can put in, and this cannot scale exponentially. This only will scale, I think, this will not scale exponentially. And because of that, it fails as the PUFs that the research paper wanted it to be. This is a cool design, but again, the issue with it is that without a very vast amount of inputs and it being exponential, it's not going to be secure. It's going to be easier for hackers to replicate, even if it is technically more complex. Now, we're talking about the advantages of PUFs in general. PUFs are a good system. They are simple and they are hard to hack because of those two points. I'm going to go on about how good and how simple PUFs are, but I would first like you to think some of your own based off what I've said in the past 13 minutes. So I'll stay silent for 10 seconds. We can think about different things that make PUFs good. Okay, now that we have determined what makes different PUFs, or what's the advantages of PUFs, I will now state some that I have seen based off of my research and going through the research book. First of all, PUFs are simple. They're a simple system, they're low cost, you just have to fit the circuit on the silicon wafer, and it really is just limited by the amount of space you have. That makes it so that it can be expanded very easily, and it is low cost because you don't have to have the maintenance of having more memory, because you have to have more memory for the integrated circuits, because if you have less registers, it makes it easier for hackers to access them. And the next reason is that they are simple. They are simple because they rely on physical factors to determine the secret. These physical factors make it a lot harder for hackers to be able to replicate it, because they now have to physically replicate this device to be able to get a similar secret. They have to I'm sorry. And they have to replicate it in a manner that is the exact same, or they aren't going to get the secret code, and therefore they won't be able to get the RSA token and the RFID key. Now talking about some advantages, let's talk about how do PFs work with cryptographic key generation. Because ultimately, if you really want to understand how PFs work, you have to understand this. PFs first make a output bits. It makes a secret that is encoded and is set. That is decoded and combined with another PF circuit to be put into a hash value, which is then put into a key generation algorithm that then spits out the key. This allows it, even though it's only having bits of 0 and 1 and just has a very long string in them, it allows it to be translated into how RSA needs a usually 6-digit code, and it needs to be numeric. Or if another system requires an alphanumeric system, where it's a variety of lowercase letters, uppercase letters, different numbers, different special characters, it can be that. Ultimately, this value is just a secret value that then is translated into the key. Now we understand how that works. Let's ultimately talk about the advantages of the advantage of PUFs. They have low cost. It's a low cost to make because it's just a circuit that is built into a silicon circuit board that holds logic gates, input bits, and output bits, and then a way of recording them. That's all it is. So because of that, it is a low cost to make, and it doesn't have to rely on an extensive system to hide where you are getting the secret from, which the integrated circuits have to do to hide which register in the virtual memory it is storing the secret. Now another advantage is that because of this, it has decreased complexity. Because of decreased complexity, it makes it so it is, again, a lot lower cost, and it makes it so that it's easier to make for manufacturers. And because of the decreased complexity, it makes it so that more people can understand how they work. And if you understand how the system works, you can have more innovations towards it, which is a good thing for this beginner technology. And finally, it is hard to hack. It's hard to hack because you have to replicate the entire device to be even able to get the secret code. And even then, as you'll see in the next slide, you might not always get it. And again, they have to replicate all the XOR gates, all the OR gates, all the logic gates. They have to know the timings. They would have to know the input bits and the output bits. And then ultimately, they would have to catch all this information in the short amount of time the PF is actually on. And that is a hard task to do. However, can't think of one of the advantages of such a device is because there's no such thing as a device that is good at everything. And as such, there are major disadvantages. This is PUF's weaknesses. Environment. The PUF, because it relies on physical hardware, physical systems, is affected by temperature. It's affected by the environment. If someone is in the Sahara Desert and someone is in the Arctic, even if they have the same PUF, because of laws of physics, one might have a 1 bit in a certain position while another has a 0 bit, even though they're the same device. Even if the device had the same inputs, it would not be the same. Solely because it will not reach as fast in a colder environment than a hotter environment. and vice versa. And there are certain points where other RFID stuff, other PUFs can have value of other PUFs for secret values depending on if the temperature reaches a certain point. If this temperature reaches a certain point, it makes it so that sometimes those values will be the same, even though they have different inputs, and that makes it so that sometimes their inputs will be flipped and it's identical to what another device is. And that's an issue, because when two of the secrets are the same, you can come into a lot of issues where accidental hackings can happen. And that's not a good thing. Now, I want you to think of some other weaknesses for PUFs. Based off what you heard, think of some other weaknesses of PUFs, and then I will label out some of my own weaknesses that I have learned throughout this paper. Okay, now that you've thought of some weaknesses, let me name some. Because of the temperature, they are unreliable. If you have a company that is located around the globe in different locales and different climates, you can have it where a person puts in a certain value for their authentication and it's wrong because of where they are. That is not a good thing. It also isn't a good thing if you are using an RFID device to, say, get into a secure government facility that you have access to, and say this facility on this chosen day is 20 degrees less than it usually is because it's a facility, and there's a special project being worked on. Now your secret's wrong. Your secret's going to be a wrong value because it is colder there than where the other device is. That is a problem. That can cause people to be locked out of their accounts, locked out of devices, even though they're the rightful owner of that device. Another issue is that, as the paper stated, 50% of the time, the same device will have the same secret code. That's good because you want them to be very similar, but it's also not good because you don't want it to be the same 50% of the time. And the main issue I have issues with it is, again, the temperature. The temperature makes it so it's an unreliable device. It makes it so that you cannot rely on it too hardly. And even when they are the same temperature and they're different devices, there's a percentage where they can be the same secret token and you randomly get someone getting in it, whereas the secret value of integrated circuits do not have this issue because they are virtual. It's going to be the same. You don't have to worry about what temperature it is that day because it's not going to affect the value of the circuit. So again, that's the only big issue I have with PUFs. Overall, they are an ingenious device. They're cheaper than integrated circuits, and honestly, they're more secure in a simplistic way. However, there are severe downsides to it, and because of that, I cannot recommend their use. However, I do recommend looking into the paper because it is a good paper, and I missed some things that the paper went over, and I did not go in depth on other things that the paper went over. And overall, it is a very good read. Thank you so much, and have a great day.